Hey, hello everyone. Welcome to another Learning Glass session. Today we'll talk about adiabatic flame temperature again, but this time we'll add on the consideration of chemical equilibrium effect, which is important in most cases. And as as any case, when evaluating the adiabatic flame temperature, we are using the first law of thermodynamics to balance out the energy in terms of the fuel's chemical bond energy and the energy it takes to reach the final temperature, which for an exothermic reaction of burning a fuel means hotter products at the end. Adiabatic means that we're not allowing any energy to escape that fuel-air mixture. That's what happens in real life. You burn a fuel, as a bystander, you'll feel hot. Why? Because energy escaped the system. But in a theoretical situation, you can prevent heat transfer out, thereby leaving all the energy in the system. And that's the adiabatic case, and in that case, the products are hotter than they would have been if you have heat loss. So if you apply the first law, you would have no heat transfer out, and what that leaves you is a balance between the enthalpy of the products. So this should have been a P. Enthalpy of the products at some temperature, which in this case would be the adiabatic flame temperature we are interested in, minus the enthalpy of the reactants at some starting temperature of the fuel-air mixture in that case. So that's our starting point for adiabatic flame temperature, but we're going to add a chemical equilibrium effect, which requires more consideration. So in combustion reactions, the fuel rarely survives. Mainly because the high temperature breaks it down, and even though there may be a lot of excess fuel in your mixture, it breaks down due to the high temperatures. So you hardly see fuel in the products. You'll see unburned hydrocarbons, but they're not going to be the original fuel. And what you may see is some remnants of it in terms of broken down hydrocarbons. But that doesn't mean, but on the other end of the spectrum, the chemical equilibrium effect also prevents completion to full CO2 and water. So in high school and in our introductory analysis, we assumed that when we're undergoing this combustion reaction, that we're going to form CO2 and water. That's a good learning point, a good starting point, but in real life, because of chemical equilibrium effect, you rarely see that all of the fuel going to CO2, all of the hydrogens going to H2O. It does still appear, but it's not pure CO2 and water because of the chemical equilibrium effect. So we'll talk about what that is. And so when we, to analyze this, we need to learn about the equilibrium effect, which is a product is analyzed or described by a new state variable, the Gibbs free energy. And what that allows us to do is to find the composition of a mixture when it's at equilibrium. And the way that we quantify that is with the equilibrium constant Kp, P meaning it's an equilibrium constant in terms of partial pressures, you can do a Kc in terms of other units of concentration, but for our gas phase systems, Kp is the most common. And it's going to tell us the equilibrium mixture in terms of the ratio of the partial pressures of each component of the mixture. So this is the products, partial pressures of the products, all multiplied against each other, raised to their coefficient, divided by all of the partial pressures of your starting reactants, all multiplied together. But remember what I said, that the combustion reactions rarely survive in the combustion case. In some other cases, you can have the reactant survive. So this is general for any reaction. And this is your equilibrium composition here. So by analyzing Kp, you'll have the partial pressures at equilibrium, the concentration at equilibrium. And another useful thing in most analyses is to use or this all stems from the Gibbs free energy. So this is the combined first and second law, as we'll discuss, but the way that this is useful is that you can find this value in tables. So this is like a tabulated thing for each reaction. So one thing about the equilibrium constant is that the key is you have to define for a reversible So the first step is to define some reversible reaction, some mixture that's going to can possibly go back and forth between reaction and products. Combustion is not one of those, but combustion still has that, and it has to do with the CO2 and water that's in the mixture. So let's write out, okay, I'll write it here. So delta G of the reaction at a given temperature under 1 atmosphere standard pressure equals, by definition, the change in enthalpy that's related to So the definition of entropy, Gibbs free energy, it's a balance between enthalpy effects and entropy effects. So the first law versus the second law type thing. This is the balance. That's where the Gibbs free energy is very useful for. And that's what chemical equilibrium is about. So the first step is, or like one important step in this analysis, is to define for a well-defined reversible reaction, find the Gibbs free energy of that process, and this is all tabulated as well. So this would be standard, some standard, balanced, reaction. You find the values of these and the values of the Gibbs free energy from tables. So this would be the equilibrium part, where you have a combustion reaction, it goes from reactants to products, and the key to the combustion process is that the reactants, the fuel disappears, but when you apply this equilibrium analysis, in the simplest case of the equilibrium analysis, you're considering what happens to the CO2 in water, and the fact that it's not going full to the complete products. There's some equilibrium process among the products, or it's not going to be the fuel because that's long gone because of the high temperatures. Okay, with that, so let's write the first law in an expanded form. Okay. So the first law in expanded form, we have used it before, would be breaking down these enthalpies in terms of the chemical bond energy of the fuel and the products, and the energy it takes to heating and cooling to the standard state and the products and so forth. So to in an expanded yet still general would be the moles of the product times the enthalpy of formation of each component of the molecule. Okay, but so not first. Let's not break it down. Adiabatic. So this is the not breaking down. You start off with little h's and then expanding it. So that's the chemical bond energy component. And then for each part of the product mixture, you're going to have to spend some energy to heat it up to the final state temperature from the standard state. And also some energy to go from the reactant temperature to the standard state. So we worked with that before. That's the first law. So this is two of the equations we need to solve for the adiabatic flame temperature with chemical equilibrium. We apply the energy balance with the fuel, the fact that we're burning this fuel to make products. That's going to give us some, it's an exothermic reaction, so there's going to be some enthalpy smaller in the bonds. Where that energy goes is to heat up to the adiabatic flame temperature. So that's the first law analysis. But on top of that, once we form the products, nature doesn't like going to full CO2 and complete combustion of H2O because of the balance between enthalpy and entropy effects. So the Gibbs free energy is going to help us to quantify that balance. And this equation is where we go. It's going to give us the equilibrium composition accounting for this balance of entropy and enthalpy. Okay, so those are the two main aspects, but that's not enough. So let's apply this. So I wrote this first law down. Let me erase this first law. So I'll give a quick, very simple example of how all of these equations can be applied. So let's consider a very simple case, the combustion of graphite, which is carbon. So it's just something that's, I guess you could kind of think about it as coal, some solid carbon chunk that can burn. So if we combine it with one oxygen molecule, it'll burn, but in some equilibrium, or the products will be in equilibrium. So if we burn it, we're going to form some unknown amount of CO2, but it's not going to completely oxidize. You might form some carbon monoxide, a product of incomplete combustion, at some unknown amount. And have some unburned oxygen potentially. But because of this not going to completion thing, this is going to be the equilibrium mixture. So it's going to be a mixture of these three components that are going to go back and forth between each other, and we have to define what that looks like. And what happens is, if this happens, it's one way, the interchange between these three molecules is such that you have CO2 so the equilibrium mixture is due to some equilibrium process, which is a reversible process where you can have CO with this oxygen coming on and off. So the CO2 is going to dissociate back and forth. This is dissociation reaction. I don't know if I spelled that right, double check. Dissociation. So this is our equilibrium process. This is our well-defined equilibrium reaction. This is going to help us to consider the chemical equilibrium effect of burning graphite. It's the fact that we burn graphite, the graphite is gone, but in the products, there's going to be some equilibrium effect which affects the products. It could affect the reactant in some case, but in this case, there's only CO2, CO, and oxygen. So that's our well-defined case. We're going to apply the equilibrium constant, which will give us some ratios of partial pressures. And that's related to the Gibbs free energy, which is the balance of enthalpy and entropy effects, first law, second law balance. And that component of this analysis is looking this process up in a table to get some standard value. Okay, so let's do that. So the standard delta G of the reaction for this process, if we can write it, if we're going to look it up in a table, we would say for any reaction, It's a coefficient of all the products times the reaction component of the products. So you get all of the, in this case it would be CO and oxygen. You find the enthalpy of formation contribution minus the enthalpy of formation contribution of the reactants. So that's the H part. Then you balance that out with the entropy effect, the second law. And each component has an entropy effect. So this would be tabulated from a table, standard balance corresponding to this standard reaction here, according to the coefficients of the balance reaction. Okay, so go ahead and erase this now, or maybe just this part here. So let me erase this here. Okay, this is 1 mole of CO2 formed times the enthalpy of formation for CO2. I mean, this CO is a product. CO2 in this, we're starting from CO2 as we defined it. Then there's an equilibrium where it dissociates to form CO. This is a product in this case. At some temperature, it's not the standard temperature. We're at some final temperature. And the coefficient for the oxygen minus the reactants. In this case, that's the CO2. That's where we're starting off from. So that's the enthalpy effect. But then you subtract that with the entropy effect, and there's a 1 in front of here, times the temperature. So that would be the entropy effect of the products. So that would be for a given temperature, the Gibbs free energy based on the tables for a given temperature, okay? So that's what we would plug into this part of the balance. Okay? So I have this still up, that's good, because I'm going to use this. That's we can find this from the tables on this side. So this is actually Kp. It's related to this. It's also related to that ratio of pressures that I'm going to write. But notice that what we're trying to do is solve for the adiabatic flame temperature. We don't actually know that. So in this case, the temperature is adiabatic, which we don't know. This should all be temperature adiabatic. That's an unknown. That's going to be in here as part of our problem. And when we apply that definition of the pressures, when we apply that to this equation, it's the pressure, partial pressure of the CO in the mixture raised to the coefficient of the reaction times the partial pressure of the O2 in the system raised to the coefficient of the reaction. In this case, it's 1/2 over the partial pressure of the reactants, which is CO2 raised to the 1. And we don't know these partial pressures. It's actually a part of the variables that we're trying to solve. And if we convert partial pressure to mole fraction for an ideal gas, what that gives us is some unknown mole fraction of CO, oxygen, and CO2. So converting that to the total pressure and the mole fractions, what you'll get is the fact that there's this extra term of pressure left over. So this is going to be one of the reactions we need to solve for. There's some unknown temperature there. There's these unknown mole fractions here. So this is part of our equations to solve for this specific problem. Another part is the mass balances. So the mass balances will give us some insight into the variables in terms of the mole fraction. So for carbon, we know that there's X moles due to the CO2 plus Y moles due to the CO. That has to balance out to give you 1 mole that you started off with. For oxygen, that's related to the other molecules like this. So those are some 2 equations that will help us to solve this system. Two of them. Okay, the other one is going to be the first law, which we will write Okay, let's write the first law again. In this case, we started off with a carbon, graphite. The enthalpy of carbon is 0. We're burning with oxygen. The enthalpy of oxygen is 0. So the chemical bond side only has the products that you're forming, the CO2 and the CO. The other components are the stable elements, so their enthalpy of formation is 0. (298 Kelvin). That's the chemical bond energy. Then you have to balance that out with some energy to heat these up to the adiabatic. So we're assuming we started at room temperature or the standard state. This is the thermal enthalpy change. You have oxygen left over in the products, so it has some enthalpy, sensible enthalpy of the temperature change. Okay, so that's the first law balance. So the unknown variables is adiabatic flame temperature, mole fractions of each of these components, and that's 4. 3 components that we don't know, the mole fractions, and then plus the adiabatic flame temperature. That's 4 unknowns, and we have 4 equations. The first law, second law, and 2 different mass balances. So now we can solve this, 4 equations and 4 unknowns. It's nonlinear, and it is, we can't do it analytically. We would have to use a spreadsheet or MATLAB or computer code. And as we also have parameters that they're not unknowns, they're parameters that we can look up in the tables. What are those? The enthalpy of formation of CO2, CO, those are tabulated thermodynamic properties that are, if they're unknown, then that's part of the problem. But thankfully, as part of this community of scientists and engineers, we know how important and powerful these parameters are. So these properties exist. The enthalpies of formation, the entropies of at certain temperatures, the sensible enthalpies. That's the beauty of thermodynamics, that if you can tabulate these values, you can use them for, to design and analyze a wide variety of processes by using these concepts. And so in this case, we have combustion. We're taking energy, we're burning graphite in this case to get on high temperature products, which we can do mechanical work with, which is a very nice technology. And then when we form CO2, we know the physics behind it is that it's going to balance the first and second laws, which is captured by the Gibbs free energy. And this would be the equilibrium part of this. But it adds another complexity that we need to solve for. Okay, so we'll have to solve this numerically. So how do we do that? As rocket scientists and others have figured out in terms of trying to tackle these problems, is they tabulate these. So, okay, tables. What tables do we use? We have to build a code to solve these equations, which exist, and we're going to do some reacting flow modeling in class on a commercial package later in the semester. And what the commercial packages do is they use rocket science. So there's 2 types. There's something called the JANAF table. JANAF table is, it's just a table for each component. So this is one example. So for hydrogen, it looks like this. So you say, okay, hydrogen. Then you just list all the properties. For some temperature, some Cp as a function of T, some entropy as a function of T, some enthalpy change, sensible enthalpy change, some enthalpy of formation, running out of space here. Enthalpy of formation and entropy of formation. So yeah, it's just a table with all of these useful values. Let me see. So it's a table starting like from 300 all the way down to 2500 Kelvin. So it's just a literally lookup table for each component, and you would get in the back of your book has these tables, the Turns book, in JANAV format, in the sense that it just has columns which are useful for many reacting flow computations. This type of analysis we're doing now from a thermochemistry perspective. This would be an example of a JANAV table. In terms of a more compact form than this, there's a table called NASA polynomials, and it's very useful because you can do rocket science with some in a compact form. So NASA polynomials, that's what I use. That's what this commercial software package we'll use later in the semester uses to find all these parameters, which are very useful for this to design combustors and analyze a lot of reacting flow processes. Is literally came from a punch card. So if you don't know what a punch card is, Google it. A punch card is a card that you punch, which came from the olden days before even analog, or yeah, it's a part of the computation where you, instead of having a flash drive or instead of having the cloud to set up, to store instructions, you would punch a card and the pattern on that card will give the computer instructions. So that was the olden way to do it, and what this card looked like was it had 4 rows, and the first row was kind of like the information. It said CO2 and like some references and some other information. The second row is where the numbers were, and for example, for CO2, it's something like 0.463218, some very precise number in this computer notation, and that would be A1. And I'll tell you what this A1 is. So it's a row so this will be where the number of A2 is. That looks like that. And then it will start over again with another set of A's. So all of this for that was because that was the NASA polynomial, where from these coefficients you can get all of the information in that JANAV table in a compact form. So that's what's so cool about it, is that these rocket scientists, they found a way to give you all the information in the JANAV table from this little set of four rows, like 7 columns or so, And the way that they can do that was they fit these thermodynamic properties in a compact form where these coefficients, these A1s, A2s, A3s, were related to thermodynamic properties, for example, like this. So that's the specific heat, but entropy is similar. You just needed more properties. So if you knew A1, because entropy is related to heat transfer, and you can relate heat transfer to change in enthalpy, and in that way it's related to entropy, so that's how it's related to the same polynomials, the same coefficients. And this is where these factors of 3 and 4 come in. It's the integral of Cp. So there's more to it. I won't bother writing down this whole thing. But that's how these rocket science compactly express this big table into this. And the reason why there's 2 rows here is because the first set was for high temperature, like from, I don't know, 1500 to 3000 Kelvin. And the second set was for low to mid temperature. So that's where we got, the whole package, where we knew that we needed the first and second laws to capture the chemical bond energy. Then we have these equilibrium effects, especially at high temperature. We need to balance this Gibbs free energy. And we put together this set of equations. And there was a lot of variables there. And for the power of thermodynamics, if we knew the properties of these molecules, like the enthalpy of formation, the sensible enthalpies, the entropies, the heat capacities, if we tabulate them if we just build a database, we can solve a lot of these problems. So rocket scientists needed those, and what they did was they built JANAF tables and NASA polynomials, and those are 2 ways of doing it. NASA polynomials is more compact. It uses these coefficients here for the polynomial and so forth. So that's how you would go about solving these problems. And you can see, even just for CO, I mean, graphite, just 1 carbon, we had this 4 unknowns and 4 equations. When you have a more complicated fuel, you'll have much more unknowns, which will give you more mass balances, but it still gets pretty daunting in terms of trying to solve it. That's where all of these nice compact forms and computer codes are necessary. So we'll learn about those codes coming up. But that, for today, it's just a good example of how to do this analysis. So thanks, and I will see you next time.